Congratulations to India on this 75th year of independence. This is a wonderful occasion to celebrate and showcase India's cultural contributions to the world, and in particular in mathematics. And so what I thought I would do today is say a little bit about the contributions of India to mathematics that are not just the one that everyone knows, namely zero. So hopefully you can see my screen. So what I want to talk about today is beyond zero. We all know about zero as one of India's fundamental contributions to mathematics, but I want to talk about a survey of some of India's contributions that go beyond zero. The current reality, even after 75 years of independence, due to propagation of colonial era textbooks and writings, Indian roots of mathematics remain largely unknown to the general public. And so unfortunately, many of India's fundamental contributions to mathematics are generally not covered in school textbooks. I personally was lucky to have learned a lot about the mathematics of India as a child, because my grandfather, my Nanaji, was a Sanskrit scholar. And so much of what I learned about mathematics growing up was through what he and my mother taught me from the various copies of ancient works that were on Nanaji's shelves. But as I was learning these gems of Indian mathematics from these ancient works, I would then go to school in US and in India and learn different names, usually European names, for some of these fundamental mathematical objects and mathematical theorems that I had learned from these ancient Indian works. And I wondered, why is this the case, and what did all this mean? And of course, it means that we still have a colonial legacy that we are trying to get over. And decolonizing our textbooks is certainly one of the things we have to strive towards. But first, we have to know what are the true contributions of India to mathematics. And so what I want to talk about today is 10 contributions of India that I feel everyone should know, that should be in our textbooks, and that we should celebrate and be inspired by, and that the youth of India should be inspired by to reach new heights in mathematics. So first, I'll start with a contribution that everyone does know. The concept of zero originating in India is, of course, well known. We've all seen the t-shirt that many Indians proudly wear saying, India's contribution to mathematics is zero. And sometimes some of these t-shirts even have a subtle subtitle saying, we always knew we were good for nothing. So while the statement about zero coming from India is true, when interpreted correctly, it's only one of a large number of fundamental contributions coming from India. Sorry, I'm hearing an echo again. Oh, great. So this pun, that India's contribution to mathematics is zero, well, that's true. The notion of zero does come from India. And this contribution of zero to mathematics is, of course, recognized and taught in schools around the world these days. But most of the other major contributions of India usually go completely unmentioned, even in schools in India. In fact, sometimes in India, even less is taught about the contributions of India than in other countries. And so today I want to point out some of these other fundamental discoveries beyond zero that were made in India that we all should know, and indeed that I feel should be taught in schools. So here's the famous t-shirt that I was referring to. Zero, India's contribution to the world of mathematics. We always knew we were good for nothing. I'm sorry, but the echo is back. So here are 10 non-zero Indian contributions to mathematics that everyone should know. So the zeroth one is zero, But there are 10 more that I'd like to talk about today, briefly, a little bit about each one, so that everyone can go away knowing a list of 10 fundamental things that India discovered that I really feel everyone should know, that should be taught in school, and that are really appreciable by the public. One consequence of zero and one use of zero is, of course, the Indian numeral system, the Hindu numeral system, that we all use and the world uses to write numbers. There's also the Bodhina Pythagoras Theorem that we all learn about the sides of a right triangle. There's the mathematics of language, originating in the work of Panini, modeling languages and modeling particularly the Sanskrit language. It's okay? You can hear me all right? You can hear me all right?
Hello. Yeah, it's fine. Please carry on.
Okay,
You're
thank
audible.
you.
Perfect.
Okay,
Thank you.
Thank you. Thank you. So there's the Indian numeral system. There's the Bodhina Pythagoras theorem. There's the mathematics of language, language modeling, as in the work of Panini. The sine and cosine functions in trigonometry, the fundamental functions of trigonometry, also originate in India. The negative numbers, most people are not aware that we use negative numbers every day today, but they have their origins in the work of Brahmagupta. As our solutions to quadratic equations also have. The general quadratic formula, the solutions to Brahmagupta-Pell equations have their origins in the work of Brahmagupta. Then the binomial coefficients, the foundations of combinatorics, also have their origins in the work of Indian mathematicians and poets, as do the numbers in the Virahanka-Fibonacci sequence. Finally, the first error detecting and correcting codes have their origins in Indian works, and also the first exact formula for pi originates in the work of Madhava in the Kerala School of Mathematics. So I hope everyone goes away realizing that these are 10 fundamental contributions that originated in the Indian subcontinent. Okay, so before we move on to the 10 fundamental contributions and the non-zero contributions, I thought I'd say a little bit about what we mean when we say India's contribution to mathematics is zero. The way we write our numerals today, which are called the Indian numbers, which is called the Indian number system or the Hindu number system, comes from India. And it is perhaps India's greatest contribution to daily life, the way we write our numerals today. The ingenuity of the Indian number system is that any number, however large, can be written using only 10 symbols, namely 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. No matter how large your number is, you can always write any number just using these 10 symbols. This is a vast improvement over other numeral writing systems that were used in other parts of the world, such as the Roman numerals, where to write larger and larger numbers, one needed to introduce more and more symbols. Whereas in the Indian numeral system, only 10 symbols are needed to write arbitrarily large numbers, any number. This remarkable Indian system of enumeration, which we use today to write any number with only finitely many symbols, is truly what has made all modern science and technological innovations possible. So what is the history of zero in the Indian number system? First of all, zero, the concept of zero was in the culture of India already for thousands of years. The concept of shunyata, of emptiness, of mind, experiencing emptiness, is a cornerstone of many of the Indian philosophical traditions. And so zero was already ingrained as a concept in the culture. And so that gave the right atmosphere to develop this incredible invention, the Indian number system. The first surviving reference that we have, it probably goes back well before this, the writing of this, writing in this system. But the first surviving reference in which the Indian system of enumeration is used is in what's called the Bakshali Manuscript, which goes back to about the year 200. When using only symbols 0 and 1, instead of using 0 through 9, one can still write all numbers, arbitrarily large numbers. And that's called then the binary system instead of the decimal system, but it's the same idea. It's still the Hindu number system, except we're now using only 2 symbols instead of 9 symbols. And this binary system of writing numerals first occurs in Pingal's Chanda Shastra, also around 300 BC, and is now the basis for all computer computation. So this fundamental contribution of the Indian number system is not just the way we write numbers by hand every day, but computers also rely heavily on the same system using just the numbers 0 and 1. And that has its origins in the Chanda Shastra. The algebraic properties of the number 0 as a number in itself, like all other numbers. In the Bakshali manuscript, the 0 was actually just written with a dot. But it was Brahmagupta who said, this dot, this shunya, should actually be a number on par with any other number. And Brahmagupta's algebraic operations that the number 0 should satisfy, the identities that 0 should satisfy as a number, were first formalized in Brahmagupta's Brahmaspurta Siddhanta in 628, in the year 628. And this was the first time that 0 was not just being used as a placeholder in writing numerals, but it was treated as a number in itself, as important a number as any other number. And that was Brahmagupta in the year 628. That was an important development in mathematics, to realize that 0 is not just a placeholder, but it's in fact a number in itself. The Hindu number system was transmitted to the Arab world by around the year 800. It was popularized by the great Persian mathematician Al-Khwarizmi, who wrote this very important treatise on the calculation with Hindu numerals around the year 825. And it was also popularized by the great philosopher Al-Kindi, who wrote the treatise on the use of Hindu numerals, circa 830. And when the Persians and the Arab world was referring to the Hindu number system, the Hindu wasn't referring to a religion. It was referring to the people who live near the Sindhu River. When the sound S moves to Persia, it becomes an H sound. And so the people near the Sindhu River, the civilization around the Sindhu River, was known, the people in that region were known as Hindus. And so the number system that was coming from that region was called the Hindu number system. And that's why it has that name today. From the Arab world, the Hindu numerals were transmitted to Europe. This happened around the year 1100, after the popularization by Al-Khwarizmi and Al-Kindi. And when it reached Europe, the Europeans thus, because they learned it from the Arabs, they mistakenly called it the Arabic numerals, the Arabic number system, even though the Arabs, of course, called it the Hindu numerals. And so textbooks, even in India, later on then started calling it the Arabic numerals. This is finally being corrected in textbooks around the world over the last several years. So that's the history of 0 and how it led to the system of numerals that we use today, the Hindu numerals. Okay, another very important contribution of India was the Bodhina Pythagoras theorem, which says that if you have a right triangle and you have sides A, B, and the long side is C, the hypotenuse, then the famous theorem says that C squared equals A squared plus B squared. This is often known as the Pythagorean theorem, but of course it was also known to other cultures prior to Pythagoras, who lived around 500 BC. In fact, there's no evidence that Pythagoras or the Pythagoreans had a proof of the theorem. It's more of a legend. But the first place that we know of historically where the theorem is explicitly stated for a general triangle in just the way we describe it today is in Bodhina Shulba Sutra from around 800 BC. And it's verse number 1.45 from 800 BC. And it says that a rope stretched along the diagonal produces an area which the vertical and horizontal sides make together. There's also a verse 1.48 in the Shulba Sutra, Bodhina's Shulba Sutra, which also describes not just the theorem, but why the theorem is true. And so a proof is essentially contained in Bodhina's Shulba Sutra. For the mathematically savvy, if you read verse 1.48, you can actually see why the theorem is true. And this was very exciting to me when I was reading this as a child, that to combine different size squares, you mark out the rectangle from the larger with a side of the smaller. The diagonal of this rectangle is a side of the sum. So if you can unravel that, you actually understand why the theorem is true. And that's it's actually one of the most beautiful proofs out there when you work it out. I want to say a little bit about the contributions of India to the mathematics of language. Painini made a huge contribution in this area, in particular in the theory of generative grammars. So generative grammar is essentially a system of rules that generates exactly those combinations of sounds and words that form grammatical sentences in a given language. And this forms an important concept in linguistics and in computer science, because the given language that we're talking about that we want to generate may be a natural language, but it may also be a computer language. And we would like a way of knowing what are all the valid sentences in that language. The concept of having a large generative grammar, a large-scale generative grammar, was first discovered by Painini, who constructed a huge generative grammar with algebraic rules that govern every aspect of the Sanskrit language. Nothing like that had ever been done before, and nothing like that has ever been done since. A monumental effort and the first large-scale generative grammar. Painini's Ashtadhyayi consists of about 4,000 sutras, over 8 chapters, and it lays down a generative grammar for an entire natural language, namely that of Sanskrit. An absolutely incredible work, and for this reason, Painini is often called the father of linguistics, and of course is the earliest founder of theoretical computer science. One aspect of Painini's work, I mean, there's modeling of verb conjugation, of formation of sentences, but even on the smaller word level, there's a whole theory of phonetics that's contained in the work of Painini. And so one small part of what Painini does is the analysis of the phonetics of Sanskrit, which is indeed an analysis of the phonetics of most Indian languages. The phonetics of Sanskrit and most Indian languages is incredibly mathematical. This includes not just Sanskrit and Prakrit, but also Marathi and Telugu and Tamil. The way the phonetics of Indian languages works is incredibly mathematical. And this way that it works is common to the North Indian languages and the South Indian languages and the East and the West. It's quite remarkable. It's very special to Indian languages. And Painini and his predecessors' description of this phonetic structure of Indian languages is truly striking to a mathematician. So what happens in Indian languages is that each phoneme means a fundamental unit of sound, and equivalently each grapheme, there's a one-to-one correspondence with the fundamental sounds of Indian languages and the letters that represent those sounds. Indian languages, most of them are perfectly phonetic. And so each sound, each phoneme in Indian languages that use the Brahmi style script has 2 independent parameters by which it's completely characterized, namely the organ of pronunciation, where in the mouth or the throat, what organ you're using from the mouth to the throat to produce that sound, and then the modulation, the quality of the sound that's being produced from that organ. It turns out that there are 5 organs of pronunciation in Sanskrit. These are the throat, the palate, the roof of the mouth, the teeth, and the lips. And these 5 kinds of sounds are called gutturals, the throat sounds, the palatals, the palate sounds, the cerebrals, which come from the roof of the mouth, the dentals, which use the teeth, and the labials, which use the lips. Those are the 5 organs of speech. And then there are 11 qualities of modulation. I won't go through what each of them means because that would take a while, but there's hard unaspirated, hard aspirated, soft aspirated, and nasal. Those are the qualities for consonants. Then they're the semivowels and the sibilants. And then they're the simple, long, gurna, and vriddhi vowels. These are the 11 kinds of modulation for each of the kinds of organs of speech. And what's amazing in Sanskrit and Tamil and all these Indian languages that use this phonetic system is that if you specify which organ of speech and which modulation, that specifies the sound. It's like a perfect 5 by 11 table. And it roughly looks like this. And most of the sounds of these possible 5 by 11, in other words, 55 possibilities, of these 55 possibilities, 51 actually exist as distinct sounds. So for example, if you're specifying, you want to know what sound comes if you use a guttural sound, if you use the throat and it's hard and unaspirated, you get a ka. But if you take a hard aspirated using the same throat, you get ka. If you do a soft unaspirated coming from the throat, it's ga. If you use a soft aspirated, it becomes gha. And then if you have the nasal guttural nasal, that's nga. And it's amazing that we actually learn the alphabet this way in Indian languages. Ka, ka, ga, gha, nga. And then we move on to the palate. Cha, cha, ja, ja, nya. And then we move on all the way to the labials. Ba, pa, ba, bha, ma. And so the labial, if you use your lips and you make a nasal sound, what sound do you get? If you use the lips and your nose, you get ma, ma. So for example, the labial nasal sound is the ma sound. And it's remarkable to most people who don't grow up with Indian languages that when they hear somebody saying the alphabet in an Indian language, they're amazed that it's a lesson in phonetics. If you think in English, for example, the vowels and the consonants are all mixed up and the organs of speech are going all over the place. But in Indian languages, we actually, when we learn the alphabet, we're actually learning a lesson in phonetics. Ka, ka, ga, gha, nga, throat. Cha, cha, ja, ja, ya, palate, and so on, all the way up to ba, pa, ba, bha, ma, using the lips. So this is a lesson in phonetics that was already written down in Bainani's time. This is how Bainani discusses the whole system of phonetics of the language. And that is then the basis of further operations such as sandhi, how to combine sounds to make new sounds. So that whole theory of phonetics really created a revolution in modern phonetics when the West learned about this system of phonemes and phonetics of the Indian languages. Okay, so that's the story of how mathematics and language really interacted in ancient times. And I'll say a little bit more about that in a couple of minutes. I want to say something about Aryabhata and his influence on trigonometry. The sine function has its origins, and the cosine function has its origins. These are the fundamental functions of trigonometry. They have the origins in the work Aryabhatiya of Aryabhata. Indeed, both functions, sine and cosine, can be traced back to the functions jya and koti jya as introduced by Aryabhata in the year 510. So this jya and koti jya, the word jya or jya ardha, meaning half chord, was transliterated from Sanskrit to Arabic when geometric works were being translated from Sanskrit to Arabic, when the geometry works of India were moving to the Arab world. It was transliterated kind of arbitrarily as jibba. Jya became jibba, just as a transliteration, not because of any translation, just transliteration. Similar sounding word. And then when Arabic geometry was moving to Europe, Robert of Chester was translating this Arabic work on geometry, and they saw the word jibba, which came from Aryabhata's jya. And jibba is a meaningless word, but he confused it with the Arabic word jaib, which means bosom. And so the Latin word sinus, he used the Latin word sinus for bosom, and that was used for the half chord function. Series of accidents. And that's how the word became sine. So Aryabhata's jya eventually became the word sine through this interesting etymology, this interesting transition from India to the Arab world to Europe. And now we all use the word sine, but it has its origins in Aryabhatiya. And this is really a testament to the importance of Aryabhata's work on trigonometry, his foundational work on trigonometry that really led to his two functions being the main functions of trigonometry that we now use today. The negative numbers. After recognizing 0 as a number, as I mentioned before, Brahmagupta treated 0 as any other number. But then he realized if you take 0 and subtract 3, that has to be a number too, if 0 and 3 are legitimate numbers, and he wants our set of numbers to be closed under subtraction, then -3 also has to be a number. And so after recognizing 0 as a number, Brahmagupta was naturally led to defining and recognizing negative numbers as actual numbers and on an equal footing with positive numbers and 0. He used an analogy with fortunes and debts to justify that both are possibilities and both are numbers on an equal footing. The algebraic properties of negative numbers were first formalized and described in Brahmagupta's Brahmaspurta Siddhant in the year 628. So, for example, in Brahmagupta's list of rules that negative numbers satisfy, he explained that just like a positive number times a positive number is positive, also a negative number times a positive number is negative, and a negative number times a negative number is positive, and so on. He described the rules of addition, subtraction, and multiplication. Nowadays, we say that the positive whole numbers, together with 0 and the negative numbers, using Brahmagupta's rules for addition and multiplication, form what in modern times we call a ring. And this is now a very important concept in modern algebra, the concept of a ring, but it would not be possible for this ring to exist, to be closed under addition and multiplication, if we hadn't added to our number system on an equal footing the numbers 0 and the negative numbers. So negative numbers also originate in India in the work of Brahmagupta. The introduction of 0 and then the negative numbers to our number system is indeed one of the great leaps forward in the history of mathematics. So when we always remember that 0 came from India, natural extension of that, the negative numbers actually also came from India as well. Brahmagupta did many incredible things. One other thing that Brahmagupta did in the same work, Brahmaspurta Siddhant, we all learned in school that the solutions for x of the equation ax squared plus bx plus c equals 0 are given by this quadratic formula, minus b plus or minus square root of b squared minus 4ac over 2a. And while solutions of this quadratic equation had been obtained geometrically, and for specific types of quadratic equations in Greece and in Egypt, it wasn't until the very first explicit statement of this quadratic formula by Brahmagupta that we really had the quadratic formula in its modern form. The first explicit statement of the two solutions for a general quadratic was given by Brahmagupta in 628 in his Brahmaspurta Siddhant. And a translation of what he wrote, to the negative of the constant coefficient multiplied by 4 times the coefficient of the square, add the square of the coefficient of the middle term. The square root of this minus the coefficient of the middle term being divided by twice the coefficient of the square is the value. And if you unravel that, you'll see that it's exactly this quadratic formula. Right? You can see to the negative of the constant coefficient, that's minus c, multiplied by 4 times the coefficient of the square, that's a. So that's minus 4ac, there it is. Add the square of the coefficient of the middle term. There it is, add the square. The square root of this right, minus the coefficient of the middle term, that's this, being divided by twice the coefficient of the square is the value. So that in words is exactly this quadratic formula. Except the way he writes it here is so poetic that you just immediately remember it when you read it in the original Sanskrit. It's very, very beautiful. Other kinds of quadratic equations that Brahmagupta solved include the Brahmagupta-Pell equation, which Brahmagupta, together with the later work of Bhaskara, fully solved the Brahmagupta-Pell equation. That's a quadratic equation that looks like x squared minus ny squared equals plus or minus 1. This equation is of great modern importance in algebraic number theory, and it was first solved in India. It was defined and first solved in India, and its importance is really felt in modern mathematics. Okay, so that's the solution to the quadratic equation, also first written down explicitly in India. There's one other beautiful interaction between mathematics and language that I want to tell you about quickly. As in many modern Indian languages, Sanskrit and Prakrit poetry consists of syllables that are classified as either short or long. In other words, laghu or guru, short or long. It's not just Sanskrit and Prakrit. Modern languages have this dichotomy of their syllables as well, including Marathi and Telugu. And so when poetry is read in Marathi or Telugu, all syllables are either short or long. And what does short or long mean? When pronounced, a short syllable lasts 1 beat of time, and a long syllable lasts 2 beats of time. So a long syllable takes exactly twice as long to say as a short syllable. And a question that arose for ancient poets, a very practical question for a poet: how many rhythms, how many meters can one construct of, say, exactly 8 beats, consisting of short and long syllables, where a short syllable takes 1 beat and a long syllable takes 2 beats, right? So 8 beats could be long, 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 or it could be short, 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 or it could be something in between, short, long, long, right? So short, short, long, long. Short, 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 long, long. So all sorts of things. Short, long, long, short, long. So all sorts of combinations are possible. Poets in ancient India came up with a very ingenious solution to obtaining an answer to this question, which is now part of a huge mathematical and artistic theory. How do you tell how many total ways you can fill 8 beats with just short and long syllables? The solution was given by Virahanka in his work Vrittajati Samuchaya in the year 700. And his elegant solution was as follows: write down the numbers 1 and 2, and then each subsequent number is obtained by adding the 2 previous numbers. Then the nth number will give the number of rhythms having n beats. So we write down the numbers 1 and 2, and then we keep writing down the sum of the previous 2 numbers. 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, 13 plus 21 is 34, 21 plus 34 is 55, and so on. And now if we want to know how many rhythms there are having 8 beats, we just go to the 8th number, 1, 2, 3, 4, 5, 6, 7, 8. And I put this in a rectangle because that is the solution for the number of rhythms having 8 beats. There are 34 such rhythms. And that's Virahanka's elegant solution, and the set of numbers that he gets are called the Virahanka numbers, defined by Virahanka in the year 700, or perhaps even earlier. In India, of course, these numbers are known as the Fibonacci numbers, after the Italian mathematician who studied them about 500 years later. I should mention that the Virahanka numbers, were also studied after Virahanka by Gopala in the year 1135 and by Hemachandra in the year 1150, again in the context of poetry. And so Fibonacci was not only was Fibonacci the first person to study the Virhanka numbers, but he wasn't the second or the third. At least 3 people, Virhanka, Gopala, and Hemachandra, studied these numbers before Fibonacci. Yet in India, we still call them the Fibonacci numbers. But the above story about poetic meters is a very beautiful and natural way to learn about the Virhanka Fibonacci numbers, because that's the way that they were really first discovered. These numbers were discovered in an artistic, poetic context, which really illustrates the fine line between science and art. And it's just a wonderful lesson to see that interaction between science and art. The story of the Virhanka numbers. A related question that comes up in the same context is, well, suppose we want a meter of 8 syllables where we specify how many laghus and gurus there are. For example, we may ask, how many meters of 8 syllables are there consisting of 3 laghus and 5 gurus? And in general, we can ask, how many meters are there of n syllables having k laghus and n minus k gurus? Again, another natural question in poetry. And the answer in this case the solution to this problem led Pingala around 300 BC, as well as later writers, Virahamira, Virahanka, and Halayudha. It led them to the discovery of Pingala's Meru Prastara, which is an infinite mountain of numbers consisting of binomial coefficients. Binomial coefficients are the answers to this problem in general. And of course, binomial coefficients now play an extremely important role throughout probability, combinatorics, number theory, and much more. So they're absolutely fundamental to modern mathematics. And Pingala and his successors gave an algorithm to produce the answers to this question in general. But in the year 850, the mathematician Mahavira gave a direct formula for all the binomial coefficients, namely the formula, if you go to the nth row of the Meru Prastara and you take the kth element of that row, that number will be n factorial divided by k factorial times n minus k factorial. We all use this in probability and combinatorics, this formula. We rarely learn that it originated in India with the work of Mahavira, but actually this originates in India as well. In India, of course, Pingala's Meru Prastara is called Pascal's triangle, after the French mathematician Pascal, who lived about 2,000 years after Pingala. And again, Pascal was not the first person to study Pingala's Meru Prastara, and was not even the second or third or fourth or fifth. Yet somehow the name Pascal's triangle has stuck. But hopefully these things will change over time as we learn the correct history. There's a whole theory of error detecting and correcting codes that comes out of the work of Pingala and his predecessors and successors, which I won't get into in detail. But the desire to maintain the integrity of metrical compositions led Pingala, around the year 300, and even by his predecessors, led them to certain error detecting and correcting codes, such as Yamatara Jabhana Salaga, that enabled the oral preservation of compositions for centuries without any errors. It's quite a remarkable error correcting and detecting code. It worked brilliantly. We have over 200 compositions in their perfect sequence of longs and shorts, laghus and gurus, that have been preserved orally for thousands of years without any errors because of these brilliant ways of detecting and correcting errors using sutras such as Yamatara Jabhana Salaga. I won't get to talk about it too much today. It is quite an intricate subject, but I've given lots of lectures about it before, and I hope you'll get a chance to look up this remarkable invention of Pingala and his predecessors. Okay, and I'll end today with talking about the first exact formula for pi that was ever known. Madhava's exact formula for pi. So we all learn about pi in school, and pi is a concept that has come up in every culture since ancient times. Over thousands of years, mathematicians from many cultures, including Archimedes, Aryabhata, Changji in China, and others, gave increasingly accurate estimates for this all-important, irrational, transcendental constant, pi, which is the ratio of the length of a circumference of a circle to the diameter of the circle. And pi is about this number here, 3.1415926533589673238846264338479713993751058209, and so on. So that's the approximate value of pi, but it's not exact. I just said so many digits, and I'm still not exactly saying pi. Pi is just approximately that. And mathematicians over many centuries, many millennia, were getting closer and closer to the value of pi, but we're never exactly reaching it. Because pi, as I said, is irrational, and it's transcendental, which means that there's no way of describing pi in a finite formula, in a small formula, just using whole numbers. So how can we write down pi exactly? The first exact formula for pi was given by Madhava in around the year 1400. And his remarkable formula, if you haven't seen it before, he showed that pi is equal to 4 times 1 minus a third, plus a fifth, minus a seventh, plus a ninth, minus an 11th, plus a 13th, minus a 15th, and so on. So since pi is irrational and transcendental, there's no way to have a finite formula using whole numbers for pi. But Madhava's brilliant idea was to write down an infinite series that gets pi exactly on the nose. And that was the first time that an exact formula for pi was ever given. That means that in theory, if you take this out far enough, you can get pi to an arbitrary number of decimal places. So this is an exact formula for pi, and the first time that was ever achieved. That was done by Madhava. So this is the first and perhaps the simplest and most beautiful exact formula for pi in history, and it has its origins in India. First formula for pi. It was discovered by Madhava in the context of his theory of infinite series, and see Professor Ram Subramaniamji's talk later today on this very topic. But it's this theory of infinite series of Madhava which indeed laid the foundations of calculus that would be discovered by him and the Kerala School of Mathematics. So that's another beautiful chapter in India's contributions to mathematics, calculus and infinite series. So there you have it. These are my favorite 10 contributions of India to mathematics that I feel everyone should know, that all our students in schools should learn. They're all very beautiful, all very fundamental. I hope it'll inspire you to learn more about these, and I hope it'll inspire the students of India to learn this legacy of their country and to be inspired to take mathematics to greater heights. So thank you very much, and I'll stop here. Thanks very much for your attention. Namaskar.
Thank you, Professor Manjul Bhargav. Thank you so much. और अब हमारा आग्रह है प्रोफेसर GS मूर्ति, नेशनल कोऑर्डिनेटर ऑफ इंडियन नॉलेज सिस्टम्स फॉर मिनिस्ट्री ऑफ एजुकेशन एट AICTE, टू काइंडली प्रपोज वोट ऑफ थैंक्स. कृपया आभार प्रकट करें.
Before that, I think let's take a few questions if there are any. So, anyone in the audience? Can I have a mic there, please? Let's see if there are any questions online too. Thank you so much, Professor Bhargavaji. Namaste. It was a pleasure interacting with you online, but nice seeing you in person.
Thank you so much for having me.
Thank you so much for having me.
I just want to take this opportunity to thank the Ministry of Culture.
There is a question, Professor Bhargava wants.
Sure.
भार्गव जी नमस्कार। मैं राजीव
नमस्कार।
कुमार।
नमस्कार।
भार्गव जी आपका बहुत इंटरेस्टिंग लेक्चर था, बहुत जानकारी मिली। मैं एक जनरल मेरा एक आपसे क्वेश्चन है कि जो इतने इंटरेस्टिंग एस्पेक्ट हैं मैथमेटिक्स के, एंशिएंट मैथमेटिक्स के, आप नेशनल एजुकेशन जो पॉलिसी बनी उसके भी एक पार्ट थे, इनको हम अपने स्कूल करिकुलम में इंटरेस्टिंग तरीके से किस तरीके से ला सकते हैं कि जैसे यहाँ पर जो बच्चे भी आए हुए हैं, स्कूल से भी आए हुए हैं, उनको ये सब चीजें जो हम आज बता रहे हैं वो स्कूल लेवल पे ही उनको बहुत क्लियरिटी हो। जैसे बहुत सी सीरीज हैं या फॉर्मूले हैं जो इंडियन ओरिजिन से हमारे आए हैं, बाद में हमने डिफरेंट नाम से उनको अपने करिकुलम में रखा हुआ है, कैसे उसकी जानकारी हम अपने बच्चों तक एक स्कूल लेवल पर ही ला सकते हैं? थोड़ा आपका कुछ सुझाव इस बारे में होगा?
हाँ, तो ये जो कहानियां हैं, लघु गुरु, मात्रा वृत्त, अक्षर वृत्त, ये बहुत सुंदर कहानियां हैं जिससे विरहांक नंबर्स निकलते हैं, जिससे बाइनोमियल कोएफिशिएंट्स निकलते हैं, जिससे एरर करेक्टिंग कोड्स निकलते हैं। ये सब कविता के माध्यम से निकलते हैं। तो हम साथ में कविता भी सिखा सकते हैं, साथ में गणित भी सिखा सकते हैं। इससे ज़्यादा सुंदर क्या हो सकता है? और जैसे हम अभी सिखाते हैं, फिबोनाची नंबर्स सिखाते हैं, वो ऐसे सिखाते हैं कि रैबिट्स कैसे मल्टीप्लाई होते हैं। एक वो इंसेस्चुअस स्टोरी है कि रैबिट से बहन भाई से मेट करके कितने प्रोड्यूस कर रहे हैं, बिल्कुल अनरियलिस्टिक है। और हमारे यहाँ जो जिस तरीके से विरहांक नंबर निकले थे वो इतने सुंदर तरीके से निकले थे कविता के माध्यम से। तो हम ऐसे अगर सिखाएंगे तो बच्चों को तो रुचि आएगी इसमें। तो मुझे लगता है जो कहानियां हैं वो सच तरीके से अगर बताएं तो बच्चों को वैसे ही उसमें रुचि आएगी। पता नहीं मेरी आवाज आ रही है कि नहीं, लेकिन मेरी आवाज आ रही थी?
मेरी आवाज आ रही थी? हेलो, यस। Professor Manjul Bhargav, this was really a fantastic lecture. So I thoroughly enjoyed it.
Thank
I have
you.
one short question to you. This string Yamatara Jabhana Salagam that you have been citing, should it be conceived as a mnemonic which has been coined just for the sake of remembering various ganas? Or would we really take it as a mechanism by which we can do the error correction? How do we understand this?
Yeah, so actually Yamata Rajabhana is not in itself needed for the error correction that was taking place. If the echo could be turned off, it'd be easier.
Mute this mic, please. Can you?
Yeah, thank you. Hi, Ram Subramaniam ji. Yeah, what I was saying is that we don't actually need the word Yamata Rajabhana Salagam in order to carry out the error correction that Pingala had suggested. So Pingala wrote poems about meters in their meters with the code where each triplet was assigned either ya or ma or ta or ra or ja or bha or na or sa or la or ga, right? But we don't actually have to know the word. As long as we know that correspondence between these consonants ya, ma, ta, ra, ja and the triples of zeros and ones, as long as we know that correspondence, which was there written in Pingala, then any of the poems that had this encoding in them about each of these meters will survive the years, because we know that when you unravel that coding onto the whole poem, it coincides with the sequence of zeros and ones of the poem. So nowadays we always use Yamata Rajabhana Salaga to memorize that correspondence, but that correspondence is written very clearly in the ancient work of Pingala, and we can just use that as a lookup and then use that to do the error detection correction. And so I don't actually know whether people were always using Yamata Rajabhana Salagam or whether they were just using the encoding that was just written explicitly in Pingala. But either way, it works just as well. But it is just a mnemonic to remember that correspondence. But it's not needed for the error correcting itself. Sorry, it would have been, if I had actually explained the whole process, it would have been easier for the whole audience to understand that answer. But hopefully Ram Subramaniam ji that answered your question.
Hello, Professor Bhargav. This is Anuradha. I just wanted to thank you very much for your fantastic presentation. I was quite intrigued by the aspect of generative mathematics related to language, and the Sanskrit language, of course, in that context, and the other Indian languages with different degrees of precision. And something that I've been working with, and it's fascinating to also understand the extent of mathematics that the mind has to perform in order to decide to make one single sound in the Sanskrit language. So I was wanting to know your take on the fact that when you're trying to promote English, and like a lot of knowledge is happening in English, and language is generally perceived as a language as a means of communication primarily. But this other aspect of language, how do you think that is something that we really need to pay attention to, and how could one make a difference in our education system by focusing on this aspect and what it would do to the individuals who studied in those languages?
Yes, great question. And a very good point. We often use English and languages generally in a very utilitarian way, but not for the inherent beauty of the languages, of which Indian languages has, just an incredible level of beauty and science in a way that other languages don't. And in India, we have that treasure in Indian languages. And unfortunately, it's not taught in schools. And I think one way to really increase the interest of children in Indian languages is to also emphasize these really poetic and scientific aspects that don't exist in the languages that everyone is trying to learn for utilitarian purposes. So yeah, I completely agree with you. I think teaching mathematics through more poetry, through the science of Indian languages, through the beautiful legacy that the Indian literature has to offer, I think really can make language learning and related areas like science and mathematics and poetry much more interesting. So I hope in language learning we can bring in these really interesting and beautiful aspects.
There are a few questions from online audience. Can we take one of them, please? You can mute this mic.
Hello, am I audible?
A little bit.
Okay, so I'm Amartya Datta. Fantastic talk.
Namaste, Amartya ji.
Can you quickly tell us that this Panini's incredible system of the linguistics, how it has impacted algebra or mathematics in the form that we know it, the usual algebra and maths that we associate, whether there has been any impact. What is your view about that?
Whether the mathematics of Panini has had any impact?
The linguistics. So Panini, what you explained is more linguistics, but the mathematics that is usually understood, what is usually understood as mathematics, as algebra, etc.
Oh, I see.
The linguistics might have influenced mainstream mathematics. Any hints about that? I think it's a big topic, but maybe you could give us some hints.
Yeah, well, theoretical computer science is a major area of mathematics, the theory of computation and computability. And theoretical linguistics and generative grammar is a big part of that. When we talk about regular languages in theoretical computer science, we're asking whether we can generate strings using a given set of rules. And Panini is the first example where we are generating strings of letters, of words, using rules. It's a way of thinking that we are proving theorem. If you think of a theorem as being a valid string in the language, we are proving theorems using a given set of rules. And that's exactly what Binary was doing, giving a set of rules in order to deduce correct, valid sentences. So it's at the heart of theoretical computer science, I would say. That is the branch of mathematics that Binari's work really influenced.
So in some sense, mathematical logic, would you say something about mathematical logic also in steps in mathematical logic? Can it be said that?
Yeah, I mean, it can be thought of as a deductive system. You have a set of rules, you have a set of axioms, and then you have a set of rules, and you're trying to deduce a set of valid statements, which in Binari's case are valid grammatical sentences. So that's right. I mean, it's a deductive system in the language of mathematical logic.
Thank you.
And it's the first such that ever existed, such a...
Another question from online, please. We'll have another question from online audience. Mute this mic, please. Is it possible to fix a separate chapter in school textbooks that describe the history of mathematics? This is Dr. Sanjay Mishra asking a question online. Professor Bhargava, please unmute this. Mute this mic.
I think that's very reasonable. Sorry, I was saying I think that's very reasonable to bring the contributions of India to mathematics to students. There are two things one can do. One is to make sure that it's embedded throughout the regular school curriculum. When binomial coefficients come up in teaching probability, that's a natural point to mention the history of binomial coefficients, and in particular, the work of Pingala, Virahanka, Mahavira in that area. So that's a natural. So there are two ways to do it: either to have just a chapter where we describe all these in one place, but then also to make sure that it's embedded throughout the curriculum when relevant. So those are two things that can be done to bring out these nice Indian stories about the development of mathematics. But I think it's totally reasonable to have a chapter as well where it's all collected in one place for students to learn. But it shouldn't be done at the expense of not saying it also where it's relevant whenever it comes up naturally in the curriculum. Because all the things, for example, that I mentioned today naturally occur in the mathematics curriculum, and yet those true facts are ignored. And there's no reason for that. When it's relevant, bring it up. But then also, sure, it's good to have a separate chapter on Indian mathematics, on the contributions of India to mathematics, on Indian knowledge systems. That's also a nice way to have it all in one place as well.